Okay, thank you, and thanks for the invitation. So it's a pleasure to be back here. And I'm going to talk to you today about fluid mechanics. So I've tried to do a broad range of application, and I've tried to define all the specific elements I need, but you're welcome to ask any question anytime you want if I forgot to define something. So I would like to talk to you more specifically about the dynamics of mixed systems which are made of two layers, one layer which is turbulent and the other one which is stably-stratified. And this system has a lot of application in the atmosphere, inside stars, and also, as you will see, in the nuclear safety. So to start with, the easiest example where you have a turbulent layer adjacent to a stably-stratified one is the atmosphere. So you have a nice picture of a very nice big cloud here. So the part of the atmosphere you know where we live and which is turbulent, convectively turbulent, is the lower part of the atmosphere, which is called the troposphere. It goes from the ground to about 10 to 15 kilometers high. So the troposphere is typically where the weather takes place. So you have storms, you have clouds, you have lots of things going on in this turbulent part. But above this troposphere, you have a second part of the atmosphere, which is stably stratified. That means that the density decreases with height. So if you take a fluid particle at some level, you rise it up, and you release it, it will go back to its initial position. So it's a very quiet domain. And for example, that's where the planes fly, because it's much more quiet than in the lower part of the atmosphere. Okay, but so it's very quiet, but that does not mean that it is motionless, because the stratosphere supports waves, which are called internal gravity waves. Internal because they are in the bulk of the system, and gravity wave because the return force is due to gravity. And here you have an example of how a turbulent plume rising up impinges on the tropopause, which is the interface between the two layers, and generates waves above it. So for those who don't know internal gravity waves, I will just show you two movies. The first one is the most simple internal wave that you can have. So it's just a two-layer fluid system. You have a less dense freshwater layer here, a salty water layer on the bottom. So you have a density jump at the interface. And if you mix the top layer, it generates oscillation of the interface, as you can see here, with a given frequency, which is for freshwater, salty water, it's about a few seconds, 10 seconds maybe. So that's for a density jump. But now, if you imagine that the density progressively increases with depth, so in this tank, which is about 20 centimeters, you have freshwater at the top and a linear increase in the concentration of salt to the bottom, which is very salty. And you have, oh, you don't see it very well, but here you have a small cylinder that moves slowly up and down like this. And we look at the fluid motion by using using shadowgraphy, synthetic Sheeran, meaning that you have a source of light somewhere here that makes a parallel light rays like that. And you look at the pattern at the bottom, and what you see are the index of reflection changes due to the salt concentration as a function of time. So if you do that, so this movie is accelerated by a factor of about 10. So you see, if you oscillate, you generate wave patterns that propagate energy from the oscillating cylinder away from it. Okay? And what you might notice in this movie is that the direction of propagation of the energy depends on the frequency. If you excite high frequency waves, you have vertical propagation of the energy, and if you excite lower and lower frequency waves, it goes more and more horizontally. So those are the internal gravity waves. Okay for that? Okay, so what's the challenge here? The challenge is that you want to predict, for instance, the weather forecast in 3 days. So you have a very turbulent layer here with storms, strong winds, and so on. So you can make prediction of the dynamics of this part here. But when it impinges on the interface, it also generates waves. And those waves, even if they don't they just move back and forth the fluid particle. They also transport energy and momentum. So you cannot close the system without also taking into account what happens in the stratosphere. But you have a strong decoupling in time scale between what happens here and the waves that goes here. So typically, the period of waves in the stratosphere is about 10 minutes. So you need to look at strong small-scale motions that generate waves here, which are about the size of about 1 kilometer, 10 minutes in frequency. And those waves can also have long-term effects. For instance, they can mix or they can generate nonlinear effects that take place on years. So when you want to model this system, this coupled system, you need to take into account all this range of length and time scale. And this is a nightmare for both numerical simulation, modeling, and so on. So the big challenge is to make a predictive modeling of this system with 2 layers, including all time scale, all length scale, and the two-way coupling between the turbulent part and the stratified part. Okay, and this question, so it applies to general circulation model and weather forecast in the atmosphere. It also happens inside stars. So here you have 2 examples of numerical simulation. This is for a star comparable to our sun. And if you take a cross-section inside this star, you have a turbulent convective layer on the upper part and a stably stratified, a radiative zone inside, which is stably stratified and propagates wave. Those waves for stars are very interesting because they allow you, using asteroseismology, to probe the inside of your star, like a scanner if you want. And also, again, they can generate long-term effects on the dynamics. This is another cross-section of a massive star, and for massive star, the configuration is reversed. So you have the convective part, which is in the center of the star, and you have the stably stratified part in the outer part. And so I will start my talk by looking at this system in another configuration, so a nuclear power plant, the containment of a nuclear power plant, where you also have a 2-layer system when it comes to an accidental situation, with a stably stratified hydrogen part in the upper part of the containment, and a turbulent, a very dynamical lower part with the air. So that makes very big problem in nuclear power plant. So the big problem I'm working on with people from the French Institute of Nuclear Safety is the hydrogen risks. So I'm sure you have all done the hydrogen-oxygen combustion experiments in high school. I will just show you an example here. So in this can, you have hydrogen. It will release his finger to let the hydrogen go out, and we'll look at the combustion. Okay, so not very impressive. You just have a flame in that case. The combustion is very slow. But when you reach a critical concentration of hydrogen and oxygen, this is what finally happens. Okay? So the hydrogen goes out of the can. It is replaced by oxygen from air, including oxygen. And when you reach a given concentration of hydrogen and oxygen, it just blows out. So it's nice when you do a lecture like this. It's much less nice when it happens in real nuclear power plants. And this is something that happened in Fukushima not so long ago. So it's really an end problem, because it is when the power plant begins to have issues, the temperature goes up, and in that case, the sheath of the pellets release hydrogen. Hydrogen accumulates under the roof of the containment, and at a given proportion, it just explodes. And that's what released lots of nuclear dust in the atmosphere in Fukushima. So people working on nuclear safety knew this problem already since the 3 Mile Island problem that took place 40 years ago, more than 40 years ago. And they tried to mitigate it. And to do so, the solution was to try to mix. So by inducing, for instance, jets in the lower part, try to mix the hydrogen layer so that you never reach this explosive concentration. Okay? So the problem is that they based their mitigation on numerical simulation, and it's a very, very challenging question to correctly model the mixing of a stratified layer from turbulence. Actually, at the scale of a nuclear power plant, you cannot use direct numerical simulation. You cannot solve Navier-Stokes equation including all time on length scale. You cannot solve, for instance, the complete range of scale involved by turbulence. So what they do is that they use model of turbulence, like for instance, Reynolds averaging Navier-Stokes model, where they don't solve all the small scale, but they just solve the average of it, the mean flow, and they just model the fluctuation. And the problem, as shown by Fukushima, is that this modeling was not correct at all. So this is shown in this example. So it's from a paper in 2016, where all the safety model, they just did a scale 1 experiment, not using hydrogen, but using helium. So they took a big container, which is about 10 meters high, air at the bottom, helium at the top, and one single jet here, and one probe here to measure the concentration of helium. So those are the point concentration of helium as a function of time. And they made a blind test with all the nuclear safety codes from Switzerland, from France, and so on. And as you can see from those curves, all the simulations were wrong, and they were all overestimating the mixing. Yeah?
How can we see which is what?
Sorry.
How do we see that it's all wrong?
So this is time. This is a concentration in helium.
And where's the truth?
The point, the data points, the measurements are the points here.
Yes.
And all the curve, each curve corresponds to one given model. And it was a blind test. So you have some adjusting parameter. Each code takes its own. And you see maybe there is one here which is true for this probe, but if you take another probe, it will be wrong. Most of the curves are on the left, meaning that they predict a better mixing than what actually takes place. It's more clear? Yeah. And the conclusion of the paper was that the few conclusions are based on the observation. Does it agree or not? But we do not obtain any interpretation of the discrepancy, which is left to the individual participant. And that's exactly what we try to do. And to do that, instead of doing big experiments, we try to scale it down to a lab scale experiment, much more simple. So it's a tank, which is about 50 centimeters high. And we use salty water at the bottom, fresh water at the top, and we just have a single jet, a single injection of fresh water from the top. This is what you see here. So we put some dye, some fluorescent dye in the stratified layer. We have injection from the top here with a given velocity, and we look at the mixing from the impinging jet on the interface. Very simple configuration. And in the lab, we try to describe the physical mechanism for mixing, and we also want to give some data so that the French nuclear safety can benchmark its numerical model. So to do measurements, we use two cameras, and we do simultaneous velocity measurements and concentration measurements. So to do velocity measurements, we use PIV, meaning that we put some small particles that are advected by the flow, and we follow them using a camera. And for the density measurements, we use laser-induced fluorescence. So we put some fluorescent dye in the bottom, and we measure the evolution of the concentration of the evolution of the light intensity, which is related to the concentration of the dye. So with that, we can have maps like this, where the arrows show you the velocity field, and the color scale, the density anomaly compared to the equilibrium state. Okay? So Reynolds number are about 1,000, and the Freud number, which is a ratio of the advection, so the turbulence compared to the stratification, is around 1. So the Freud number is about right compared to the industrial application. The Reynolds number, obviously, since we are much smaller, the Reynolds number is also much smaller, meaning that we are less turbulent. But what we want to do is already to test the model on this simpler case. Okay, so it's a very simple problem, and it's actually a long-standing subject in research. So you have paper of this simple configuration since at least 40 years. And what I show in this graph is a compilation of all the results showing you the erosion rate as a function of the Freud number. So again, the Freud number is a ratio of the velocity of the turbulence divided by the stabilizing effect, the stratification. So you see, when you increase the advection, you increase the erosion rate, and you have various scaling laws. It depends on the interpretation of the data. With the scaling, with a power 3, a power 2, a power 1, you have all kinds of models. But all those models are all based on the same underlying physics. So the physics is that when you look at your jet, you have a mean flow. So the flow, on average, on the time average, it comes from the top. It just impinges, it deflects the interface, and then it spreads on the side. So from a mean flow point of view, you have a strong shear along the interface, and a strong shear in fluid mechanics means that you have some instability, so Kelvin-Helmholtz type instability. And this instability generates lots of small swirls, if you want, that induce mixing all along the dome. That's the basic underlying physics here. So we can test this simple model by using our data. The problem is that to have this type of instability, we need to reach a threshold, meaning that we need the shear to be strong enough compared to the stratification. And this threshold is about 1/4. And when we do measurements all along the radius of the dome here, we see that the Richardson number is always larger than typically 3. So we are always below the threshold. This situation is never unstable for the Kelvin-Helmholtz instability. So the basic physical description of the mixing cannot be correct. How does it translate into the numerical modeling of the turbulence now? So I told you already that we cannot, at this scale, at the scale of the industrial configuration, we cannot solve for the complete Navier-Stokes equation with all the scales in time and space. So what people do is that they decompose the flow into two components, the time average component, the bar component, the mean, and the fluctuation. And what they do after that is that they write Navier-Stokes and conservation equation, but they only solve for the mean. So for instance, I wrote here the equation for the mean density concentration. So the time derivative of the mean concentration is a gradient of the fluxes. And you have two types of fluxes, the mean fluxes, which is a product of the density and the velocity, the mean density and the mean velocity. And then you have a flux coming from the fluctuation. Everything that is turbulent just go into that term. And then very schematically, what you need to solve your system is to get a model of this term. And what is done usually, what is done in Rand's numerical simulation, is to say that this turbulent flux is actually only equal to some turbulent viscosity times the gradient of the density. That's the most, of course, you have some more evolved models, but the most simple one, the basic one, is that. So that means if you model your fluctuation by a turbulent viscosity, or a turbulent diffusivity, sorry, it means that you will have a flux of mixing that goes across the density interface from the more dense layer towards the less dense one. So those are the red arrows here. Okay, so if we take one snapshot from the numerical results using this modeling, this is actually what we see. So this is the vertical turbulent flux. It's red all along the interface, corresponding to the sketch I just showed you. We have a turbulent diffusivity mixing perpendicular to the interface from the bottom towards the top. And we have almost no horizontal turbulent flux. That's for the numerical modeling. But now we have data from the experiment. And when we look at data from the experiment, it's not at all that what we see. What we see is that we have mostly an horizontal turbulent flux. And we have some vertical turbulent flux, but it is positive in the middle, but it is negative on the side. So it means from this decomposition point of view, you have a demixing if you want. You have a flux going from the top layer towards the bottom layer. So that's just opposite to what a turbulent viscosity, turbulent diffusivity would tell you. So that explains why all the numerical predictions were wrong. It's because they overestimate the vertical turbulent flux, and that's because they do not take into account the good physics at the beginning. Yeah? So what is the relevant physics? So with the experiments, we can have a look. So this is a real-time movie. And actually, what you see from this movie is that you don't have mixing all along the dome. You only have mixing on the side. So the true physical flow going on, it's not turbulence all around here doing mixing all around the dome. But what you see is that the turbulent fluctuation inside the dome, they excite waves at the interface. Those waves propagate and break on the side where they do mixing. Yeah?
So you speak about the dome as though it was always somehow given, but I mean, the jet impinging will also lead to some mixing, so the interface will also be varied as well by this?
So the interface vary with time, but when you look at the time average flow, you just have a mean position of the dome. And of course, on the much longer time scale, you will have a global erosion. So everything will go down like this as a function of time. So you have a time decoupling between the fast processes. When you do numerical modeling, you don't take into account this fast processing. Then you have a quasi-equilibrium state with some mixing, and then a global decrease of the position of the interface. So you have 3 different time scales. Okay, so all is in the wave. So we can now develop a new model, knowing that the physical process of mixing is not this Kelvin-Helmholtz instability all around the dome, but it's just excitation of waves, propagation, amplification, and breaking. And from this very simple basics, then we can have scaling laws. So to model the mixing, we just make an energy balance between the potential energy coming from the jet, but not directly from the fluctuation of the jet, from the waves that are excited by the jet. So the typical time scale and length scale that we need to take into account in this estimate of the kinetic energy are those related to the waves. And this energy must balance the potential energy corresponding to the mixing. You take some dense fluid, you put it higher up, so that costs some potential energy. And when you balance the two, you can have, I skip all the details, but you can find a scaling law here, which is in red, that fits well most of the data. So actually, it fits well most of the data except those ones that are here, which all correspond to this paper in '94. But this paper was a very specific configuration where the water coming in was denser. So it was just crossing all over the tank and not just going at the interface and coming back. So it's kind of specific. So we can argue, and again, I don't give you all the details, but we can argue that in our scaling law, which predicts the erosion rate as a function of the Froude number, we have adjusting parameters, and those adjusting parameters depends on the configuration of the system. But taking the same analytical solution, just changing the prefactor, we can also adjust here the curve and the transition between power 3 scaling law at low Froude number and the power 1 scaling law at higher Froude number. Okay, and we can also, so what was very specific about those measurements is that we measure some negative flux on the side of the jet, which seems strange because it's like having a negative diffusion coefficient. If you wanted to model it by a turbulent diffusion, it means that you would need to take a negative turbulent diffusion. This can also be explained by a simple model where you look at the wave breaking, so the decrease of the amplitude of the wave on the side of the dome, and if you balance the energy that comes from the decrease of the waves to induce mixing, then you actually predict quantitatively a negative flux that fits well with the experimental data. So that's pretty much where we are today. And so what are we doing, trying to do for nuclear safety? Well, so Rand's modeling does not work. So Rand's, again, means that you solve only for the time average mean flow, and you model the fluctuation. There is no way that can work using simple turbulent diffusivity model, because you will never predict this negative here. Another numerical approach is to use large eddy simulation. So large eddy simulation, it's different. It's an averaging. It's the filtering in space. It means that you model all the larger scale of the problem, and you model the small scale of the problem. But you solve it. You don't have any time averaging. So in that case, this is a numerical simulation using this new modeling of the turbulence, still from the IRSN software. In that case, you have a quantitative agreement with the experimental measurements. The problem for nuclear application is that these LES modeling are very costly. We cannot have them in the whole containment, in the whole power plant. So what my colleagues in IRSN, and Fabien Duval is leading that, is to use an hybrid approach where you use Rand's modeling everywhere except close to the interface where the mixing takes place. And in that location around the interface, you switch to an LES approach, and combining the two, you can hope to have better prediction for safety issues. But that comes with other problems that you have to deal with at the interface where you go from LES to Rand's and so on. And the experiments can also help here to describe the transition zone and to give the cutoff size where you need to switch from one to the other. Okay? So that was for nuclear safety. You don't have any question on that for now? So now I come back to the atmospheric problem. So you remember one of my first slides. In the atmosphere, you have the lower part where the weather takes place, strong turbulent motion, and you have the upper part, which is stably-stratified, where waves propagate, internal waves propagate. And you have a strong decoupling between the fast motion here, the intermediate wave motion, and you also have, from this wave motion, long-term consequences. So we saw one long-term consequence just before it's mixing, for instance. And there is another very well-known long-term consequence in the atmosphere. It's the quasi-biennial oscillation. So the quasi-biennial oscillation is a periodic reversing of the wind in the stratosphere along the equator every 14 months. So if you take the Earth, the equator band, so you have the troposphere close to the ground up to 10 to 15 kilometers, something like that, and then the stratosphere above it. And then if you measure the equatorial average of the wind velocity as a function of time, so this is depth in the stratosphere, this is time in years, and the color scale is the average horizontal wind velocity. And you see that every 14 months you have a reversal. Sometimes they all go towards the west, sometimes they all go towards the east, and you have reversal taking place every 14 months, starting at the top of the stratosphere and going down. So we have a nice phase velocity towards the bottom. Okay, so the problem is, how do you model the source of the waves? The waves have a period of 10 minutes, and then those long-term reversal on several months. That's a nightmare, for instance, in global circulation model, where you don't solve for the waves and the turbulence, but you want to look at the long-term evolution of the climate over 100 years. So this long-term effect of the waves, it has been explained theoretically in the 70s. And it's due to a specific properties of internal gravity waves, which are anti-diffusive. So it means that a wave will damp more strongly when it goes in the same direction as the mean flow, as the ambient mean flow. So on this small sketch, you start from an established mean wind flow like this as a function of depth. And you imagine that you launches at the bottom 2 waves with the same frequency, same wavelength, but one propagating towards the east and one propagating towards the west. Because of this anti-diffusive effect, these waves will damp very rapidly on this mean flow. If it damps, it means that it will deposit all this momentum and it will accelerate this wind. The wave going in the other direction will be less damped, so it will go higher up until it reaches a wind in the other direction, where it will damp, deposit its momentum, and increase its velocity. So the whole wind pattern here, this will be increased and will go towards the ground, and this will increase and go also towards the ground. And then you have a new configuration where this negative wave will damp here, the positive waves will go higher up, generate a mean flow higher up, and a new cycle will begin. So that explains the downward phase propagation of the reversal, and it just comes from this specific property of internal gravity waves. Okay, for the mechanism? So, by the way, those are real data, measurements in the atmosphere. So we can model that using a very simple equation. So this is the equation, again, for only the average, the horizontal average of the horizontal velocity. So the time evolution of this mean velocity, it evolves because of viscous diffusion. And you have a forcing term here, which is due to the Reynolds stress coming from the fluctuation. And we can model this nonlinear Reynolds stress by just saying, just describing the internal waves as linear in a WKB approach, meaning in the optical geometry limit, meaning that the length scale, the wavelength is small compared to the large scale variation in the domain. So you can have an explicit expression for this term, and then you can solve for this equation in this limit using a monochromatic one-way model. So as a function of time, I will rerun the so we start from a small, this is the velocity as a function of height. We start from a small perturbation like that, and then we permanently inject 2 waves, as in the sketch before, and we look at the evolution of the mean flow. So here, the positive propagating waves increase this, the negative one, the positive one, and this is a sketch as a function of time and depth of the mean flow. And you see with this simple equation and a linear model for the wave contribution, we predict the nice mean flow reversal with a downward phase propagation. So this model is from the 70s. The problem is that it only considers one type of wave, one propagating in the positive direction, one in the negative direction, but with the same frequency, same wavelength. Of course, in nature, you don't have only one wave. You have a bunch of waves which are excited by turbulence. So what we have done, oh, by the way, this was done also experimentally by Benoit here not so long ago using salty water experiment. And you also recover in the experiments very nice oscillation with downward phase propagation. So we want to know if this regular pattern will also appear if you consider a large range of waves excitation. So to do that in a systematic way, what we did is we solved this, but instead of having only one monochromatic wave, we consider a spectrum of waves, and we actually consider a Gaussian energy spectrum, where we conserve the integral value of the energy, but we conserve also the mean frequency of excitation, but then we spread the max amplitude and the standard deviation of the Gaussian. Okay? Okay, so this is the signal we obtain for one frequency only. You see it's not periodic, actually it's frequency locked, where you have the main frequency here, the subharmonic, and it gives you a regular but not a single frequency signal. Then if we consider a larger spectrum of excitation, this is what we see. It goes to quasi-periodic, so even more noise if you want. But the surprise is that if you take an even larger spectrum of excitation, the system self-regularizes. Actually, you obtain a very nice regular quasi-biennial oscillation with one single frequency. So somehow this strange system, the more noise you put in your source, the more organized it comes. This is kind of surprising.
You can create the flux with a WKB approximation?
So it's the same as Plumb. So it's just WKB, but instead of having one source, we sum the source, yes. And we do not look at the cross correlation because in the WKB, the cross correlation with average to zero will go to zero on average. So we have drawn a Poincaré map here. So those are phase space trajectories. So we measure here the velocity at a depth of 0.5, here the velocity at a depth of 0.1. And in that case, when you have a very regular configuration, periodic configuration, you just have a square. And then we measure this velocity when this velocity goes to zero. That gives you 2 points here. And we put those 2 points here for this standard deviation. Okay, so when you have a more complex, a quasi-periodic signal, it's in the depth, you see a more complex signal, and here it's a frequency locked regime. So you see, when you, in this Poincaré map, when you increase the standard deviation of your Gaussian excitation, you go from frequency locked to quasi-periodic to periodic. So having more noise gives you a more regular signal. So is it that surprising? Actually, not really. So we have done other systematics. So in that case, those are the same types of Poincaré map. But here, we fix the central frequency. We fix the energy and the standard deviation, and we increase the central frequency. So when we go for waves to low frequency, we have no QBO. We are below the threshold for instability. Then we have a chaotic signal. And then when we go to higher frequency, we recover the regularity of the reversals. So when you excite higher frequency waves, you have a more regular QBO. And that's because, if you remember my introduction, high frequency waves mean that waves propagate energy very in the vertical direction. So you can have a lot of energy that makes the QBO from the top, and then it can go down. So really, the QBO is controlled by the higher frequencies that you excite in your system. This other Poincaré map is changing the energy for a fixed central frequency and a fixed standard deviation. And you see, when you are at low frequency, you have a regular signal, but when you put more energy in your system, it becomes more chaotic. So that's normal. That's a kind of not such a surprise. So what we do when we have these Gaussians that we spread, we put more and more energy into high-frequency waves, but we put a low amount of energy in high-frequency waves. And that since these waves at high frequency goes higher up, those are the ones that control the QBO, and then they just cancel out the contribution from all the other waves, and you get a QBO. So when you spread a given amount of energy over a larger spectral domain, you give low amount of energy to high-frequency waves, and then you organize your flow. OK, so I told you that the most important point when you have a turbulent spectrum of excitation of the waves are the higher frequency waves. So it means that you don't really care about your spectrum of excitation. And those are 3 examples of the QBO you get from various types of turbulent spectra. It's a Gaussian turbulent spectra. It's a Kolmogorov type with a K-3. Here it's a minus 5/3, sorry. And here it's a rotating turbulent spectra with a K-3. And you see that in all cases, you observe the same results. So that's very surprising. So you don't have a unicity. If you observe a QBO signal in your atmosphere, you don't have a unicity for the source. So it means that you cannot just look at the QBO and the waves. You also have to include what generates the waves to really understand your system. It really depends also. You need to take into account your two-layer coupled system. Okay for that also? So how can we do that in the lab now? And I will finish with that. Can we have a lab experiments where we will have a two-layer system, turbulent, stably stratified, with turbulence-generated waves and waves-generated quasi-biennial oscillation also? Can we do that in the lab? So that's possible actually using water. So it was not a very complex fluid, because water had a very specific property of having its maximum density at 4 degrees. So I'm sorry you don't see very well the picture here, but just imagine you take a tank like that, 30 by 30 by 20, a regular Rayleigh-Bénard tank, and then you cool down from below at 0 degrees, and you heat from above at 35. Okay, the usual Rayleigh-Bénard experiment is you heat from below, you cool from above, and you generate convective motion. Here, I cool from below at 0, I heat from above at 35. Well, between 0 and 4 degrees, my density profile will be unstable. I will have less dense 0 degree water, below more dense 4 degree water. So I will generate convection in the bottom part of my tank. And then above 4 degrees, I will have a stably stratified layer, because the density goes in the usual direction. So just in this simple system, I can have my two-layer self-consistent system in the lab. So this is not a new idea. Actually, the initial idea was by Townsend in the 60s. OK, this is what we did. Je peux juste éteindre la lumière? Ouais, c'est pas mieux. OK, whatever. I have a picture. So this is a strict picture of the experiments. So I just take a long exposure time on my camera. I have tiny particles in the system, and I look at what comes from it. So in the bottom part, as expected, I have strong turbulent convective motion, and above it, it looks quiet. Okay? This interface is around 4 degrees. This looks quiet, but if I take a vertical cross-section and then I look from above, I do some PIV measurements. This is what I see. So this movie is accelerated 300 times. And the typical velocity we measure are about from up to 10 micrometers per second. So those are very tiny motion, but they do exist. And you see, what you see actually are, so imagine you have impinging plumes at the interface, and then you have waves, like at the surface. If you if you let a rock on the surface of a lake, you will have the waves pattern going away from it. Here it's the same, but in 3D. So you have an impinging plume, and then you have wave pattern spreading like that as a function of height. So do we have QBO? So to do that, we look from the top and we insert a cylindrical container in it to have the axisymmetric geometry. And we look at the time average flow as a function of time. So you have three measurements over 1 hour. Here it goes in that direction. Here it's an intermediate state, and then it goes in the other direction. So we do have reversal in this system. And this is the measurements of the mean flow along this dotted line as a function of height and time. And you see that we have those type of reversals. So we do reproduce QBO in a self-consistent turbulent system. So we were initially very happy with that. It's not so long ago. The paper is just published. So we were very happy, except that I insisted on the fact that the signature of the QBO is that the phase velocity goes downward. And here we just have the opposite. So what do we see here? We see a reversal, but with a wrong phase speed. It goes in the opposite direction. And actually, it is the phase propagation here is very close to a viscous diffusion. So what we see here is not a real QBO-like pattern coming from the waves, but it's just a coupling with the bottom turbulent convective layer. That was kind of disappointing. But when you are disappointed, you can still make some work. So we work with a colleague doing 3D numerical simulation of the experiment. He just reproduced the whole setup in 3D. This is, again, this graph of time as a function of time, the mean flow as a function of depth. So you have the convective layer, the stratified layer here, and you see when the numerics reproduce the experiment, you do see this viscous type coupling between the two layers. So it's a failure, except that there is one big difference between our system and the atmosphere. And this is an additional dimensionless parameter that I have not talked about at all yet. It's the Prandtl number. The Prandtl number is a ratio between the viscosity and the diffusivity. And for water, it is fixed at 7. So it means that viscous effects are more important than diffusive effects. So Prandtl is 7 here. Viscous effects are important. You do see viscous coupling. But now with the numerics, you can just turn the button and, for instance, choose Prandtl number of 0.1. And in that case, what you recover, all the parameters are the same, the Rayleigh number and so on. The Prandtl number, you recover this QBO-like effect. So really, this is important for instance, for atmospheric modeling, but also for stellar modeling. Most of the numerical simulations, they use a Prandtl number of 1. And here it's a perfect example where you see that Prandtl number of 1, it's not correct. I have another example just after here. It's another example with a Prandtl number of 1. At 1, you don't really see reversal. You see something, but not really reversal. You really have to go to lower Prandtl number to see the good signature of your system. So yeah, it's a message for people doing atmosphere, stellar interior dynamics. You don't want to take Prandtl number of 1 if you don't want to look at some long-term dynamical effects. And I'm actually running out of time already. 5 minutes. Qu'est-ce que j'ai? Okay, so just to mention a last application, this time in star. So one big question in star. So I told you already about asteroseismology. People in astrophysics, they use light fluctuation at the surface of the star to induce, to get information about what happens inside the star. In the deep interior, you have no access except from the signal of wave oscillation that you see at the surface. Okay? And internal gravity waves are very important because they go deep. For instance, in the sun, those are waves that propagate in the stratified zone in the deep interior of the star. So they are very useful because they can probe, like a scanner which probe in the deep inside the star. And for that, it's very important to know what is the flux excited by the waves. So to get a model of this, we perform some 3D numerical simulations. So those are very extremely costly numerical simulation. And you see again, so this is a vertical velocity. This is a temperature anomaly in two vertical cross-section. And those are horizontal cross-section in the convective zone, at the interface, and in the stratified zone. Okay? So using those, we can compute flux, energy flux, and the spectrum of waves excited by this convection. The typical Rayleigh number here is 4 to 10 to the 7. And it is a big question right now in asteroseismology, in astrophysics, to know what would be the spectrum excited by turbulence. So using those numerical simulations, we have tested one of the models, which was developed by my colleague Daniel Le Cohanet during his PhD, which predicts that the wave energy goes like k to the 4, so the wavelength and the frequency minus 13/2, and that the wave energy decreases like the distance with the power minus 13/8. So this is a very strange exponent. However, you see that the dot line is the theoretical law. The points are numerical simulation for various value of the strength of the interface and for various value of the Rayleigh number, the intensity of convection. And you see that we have a very nice agreement between the two. And we have used that very recently for ongoing debate. So there were last year observation of very massive star. So massive star means that the waves are in the upper part and the turbulence in the inside. There were a lot of new observation of those stars where they showed that they have some low frequency photometric variability. And the claim of these people, so Bowman and co-worker, was that those low frequency waves were internal gravity waves, stochastically excited by convection. And so from that wave, they can have some probe of the interior. But looking at the data, we could show that it did not fit with our prediction for the excited spectrum. And so it could not be internal gravity waves, and so it has to be another model. And Daniel proposed that it was some sort of subsurface convection. So I just mentioned this because I like the back and forth interaction between theory, experiments, numerical modeling, and data, and that's what I try to do in my research. So now I don't have time anymore, so I will just finish with those 4 movies, saying again that there can be strong benefits on a multi-method and interdisciplinary approach, even on a old question and old science like fluid mechanics. And I thank you for your attention.
Okay, thank you, Michael. So we have time for question.
I have a very elementary question. What leads to such a sharp cutoff between this stably stratified region and the turbulent region? I mean, why isn't this more gradual?
So in stars, it's very gradual. Actually, it depends on the slope of the density stratification. You can imagine that if you have a strong slope of the density stratification, you will have a very sharp interface. And if you have a smaller slope, and it can go higher up. So we have done a systematic study of that here. So for water, you don't have choice. This is the density, how would it look like with water. And if you want the slope in the convective zone, is the same as the slope in the stratified zone. But then numerically, you can choose one given slope for the convective zone, and then you can change the stiffness of the interface, changing the slope of the density variation with height. So S is the stiffness. And when the stiffness is very large, you have a very sharp interface. When the stiffness is like water, you have a sharp interface, but with some fluctuation. And when the stiffness is small, of course, you overshoot completely, and your rising plumes, they just mix the whole stratified layer. So you have a whole kind of possibilities. It turns out that in stars and in the atmosphere, we are more in that case, close to the intermediate case, where it's mobile, but it's not, it remains on average stable. What is interesting, I find, is that even in that case where the interface is very sharp, you still have waves propagating on the top. So it's not only the interface distortion that generates waves, it's also the turbulent coupling with the turbulent motion below that generates waves that propagate up. And that's also a long-standing open question in atmospheric science, for instance. What is the source of the waves? Is it the interface distortion like that, when you have a plume that comes and distorts the interface? Or is it the turbulent fluctuation inside the convective layer that somehow generates, projects onto the waves that propagate them? So this is part of the answer. Actually, the most important contribution are those Reynolds stress from the convection that generates waves, and it's not the distortion of the interface.
Est-ce que tu peux décrire un peu plus ce que ça veut dire la zone où la diffusivité est négative? Qu'est-ce que ça fait sur les grandes échelles? Et quel est le mécanisme à petite échelle qui fait ça? Ça, c'est pour l'interface.
Dans la partie nucléaire?
Ouais.
Alors la diffusivité turbulente, elle n'est pas négative. Les fluctuations vont toujours générer du mélange. C'est juste la description en termes de écoulement moyen plus fluctuation qui aboutit à un truc contre-intuitif qui serait modélisé par une viscosité turbulente négative. Mais ça, c'est parce que la viscosité turbulente ne décrit pas bien le process de mélange par les vagues. D'accord? Donc, ça paraît un peu bizarre d'avoir un mélange négatif, mais c'est juste la manière de décrire le système, et qui est basée sur la description physique de écoulement moyen plus fluctuation. Mais dans les faits, évidemment que la turbulence encourage et provoque le mélange. Ça ne va pas le contraire. C'est juste la description qui se traduit par le fait que ce serait, si on voulait la modéliser par une approche écoulement moyen plus fluctuation, il faudrait mettre un coefficient négatif à la diffusivité.
Et du coup j'en ai une autre. Est-ce que vous comprenez pourquoi à pente thermique plus petit, il y a plus de la QBO a l'air plus régulière? Ouais, donc est-ce que le fait qu'il faut s'éloigner de pente égale 1 pour avoir la QBO régulière?
Alors je pense qu'il y a toujours un effet QBO, mais il est plus ou moins masqué par le couplage visqueux qu'on peut avoir. Et ce couplage visqueux, il est évidemment un peu artificiel pour nos manips où on est à des Reynolds relativement bas.
Attends, il n'y a pas un moment où tu as expliqué que tu changeais le prente,
ouais.
Et du coup tu voyais apparaître, tandis qu'en simul, à prente égale 1, tu n'avais pas la QBO régulière, ça devenait plus régulier après, à prente plus petit? Ça, oui.
Alors là, c'est avec le même color scale pour les trois systèmes. Donc je pense que dans tous les cas, le mécanisme QBO d'interaction non linéaire des ondes, il existe. Mais là, il est masqué et il n'a pas le temps de se développer parce qu'il est d'abord contrôlé par un espèce de couplage visqueux avec... le couplage visqueux l'emporte et empêche la QBO de se développer. Et moins tu as de couplage visqueux, plus tu as le temps pour la QBO de se développer et plus tu vois un signal de type QBO fort. Mais je pense qu'ici aussi, tu vois, des fois, tu as des traces quand même de QBO qui peuvent apparaître. Mais le problème, c'est que pour avoir de la QBO ici, il faut que les ondes aillent bien haut. Et si tu as un couplage fort à l'interface, tu Doppler shift les ondes et elles ne peuvent jamais accéder en haut. En fait, elles sont filtrées à l'interface où un écoulement moyen s'est développé par couplage visqueux. C'est un peu un feedback.
Du coup, si tu pouvais monter le nombre de Rayleigh pour avoir la QBO à Prandtl.
Peut-être.
Pardon. Et si tu montais le nombre de Rayleigh, est-ce que tu pourrais voir la QBO à Prandtl plus grand?
Je pense, ouais. Donc pour l'atmosphère, évidemment, le Prandtl, il vaut 0,7 dans ces eaux-là, et le Rayleigh est beaucoup plus grand. En tout cas, le Reynolds est plus grand. Est-ce que c'est le Rayleigh? Le Reynolds est plus grand, et donc je pense qu'à 0,7 pour l'atmosphère avec un grand Reynolds, on n'a pas trop de problème. Tu vois, c'est les deux liés. Là, le message, c'est plutôt qu'on voulait faire passer. Ça c'est vraiment ce qu'on arrive de faire. C'est pas loin du top de ce qu'on peut faire en simu. Et dans toutes les simus, que ce soit pour des applications géophysiques, astrophysiques ou ce que tu veux, tout le monde prend Prandtl égale 1, parce que c'est plus facile numériquement. Prandtl égale 1, ça peut te cacher de la dynamique, quoi. Et il suffit de la descendre un tout petit peu. Tu vois, ça c'est encore quelque chose qui est accessible, je pense. Et ça peut vraiment, quand tu regardes sur le long terme, ça peut changer. Donc c'était plus un message comme ça. Prenez pas Prandtl égale 1 si on a une application. Et toutes les applications... by the way, c'est à prendre plus petit que 1, que ce soit pour les applications stellaires. Alors là, il est petit, mais aussi pour le noyau de la Terre ou pour l'atmosphère. Ah, pardon.
Just a quick question. In your introduction, you mentioned two different stellar configurations, one with the waves propagating in the interior and the turbulence outside, and then massive stars where it's the other way around.
Yeah.
But so in this helioseismology, you need to observe the waves at the surface, right?
You only observe the surface.
So if the configuration is such that the waves only propagate in the interior, that's not very practical for this.
But they can still observe them at low frequency at the surface.
Okay.
Because they are very low frequency, so you can, in the spectrum, you can distinguish between everything that comes from the convection. You have pressure waves also, high frequency waves, and the low frequency they are interpreted as a signature at the surface of the internal gravity wave in the interior. And those waves are very important for them because those are the only ones that actually scan the deep interior, the stratified layer of the sun. It's the only way to have access to this very deep dynamics. In the massive star, it's just the opposite, and you have some very nice effects that in astrophysics they start to look at. So you also have, it's compressible in the star. So when you go towards the surface, the density decreases, and since you conserve the wave, wave action, thanks, it means that the amplitude of the waves increases. So you can have excited waves from the convective zone inside, and they propagate up towards the surface, and then they break at the surface, and they can have strange effects on the stars.
I'm surprised, this thing about the Prandtl number, of, that people took 1, I understand that's easier, and 0.1 it's a little harder, but I keep hearing people here talk about, and in other kinds of astrophysics, talk about Prandtl numbers of 10 to the -6th and things like that. They couldn't take a factor of 10. This is almost like Prandtl number of 1. I'm very surprised that people found that to be beyond their means. Because I'm used to hearing of orders of magnitude difference. So these numerical calculations that are so hard to do, you're showing us a complete slice of a 3D domain here?
So those are in 2D only.
Oh, no, they're in 2D.
So I must say that when you want to do QBO, you need very long simulation.
Yes.
And in that case, we are only capable of doing it, for now, in 2D. We did one for the experiment in 3D. So the one for the experiment was in 3D. And then we did other simulation in 3D, the one I showed at the end. Those are 3D, but they were not run long enough to get the QBO.
And all of this is Navier-Stokes, no
Navier-Stokes,
LES,
DNS.
no DNS,
It's with,
complete DNS.
I should mention that.
Yeah.
Otherwise, Daniel will not be happy with me. It's done with the best code in the world, which is Dedalus, according to their author. Right. It's free, you can use it, and it's a solver of any equation you want, very powerful and very practical to use.
Is there more question? So I think we can thank Michael again.